Hello everyone, welcome back to lecture 19. In continuation, we will basically try to summarize the molecular adsorbates and the factor that are controlling the molecular adsorbates, and if time permits I will be also discussing with you the solid liquid interface, because you can also form molecular adsorbates in solid liquid interface, and we will also have a look at that, because there are certain additional interesting factors that are also controlling the final assembly of the molecules on the surface. Now, well, what we have been doing was to understand the molecule surface and molecule interaction separately, and now we have come to an agreement that one need to basically consider something like a potential energy surface which is looking more structured when you want to consider the so called molecule interaction into account. So, then you would basically have something known as the potential energy, and then generally we called this one as the delta E intra, and then we said that there is also something known as the molecule surface interaction, and of course, the molecule surface interaction is kind of periodic in nature, but nonetheless due to the fact that the molecule can have many different possible orientation on the surface similar as molecule possible orientation, that potential energy surface is also much more structured than just having a simple periodic function, as we have seen in the case of atomic adsorbate on surface. So, then if I would put that into account, then also you would find that they are much more structured. However, there is a periodicity, that something like this one can basically see. So, this would be basically the distance between the distance between the molecules between the molecules, and then you clearly see that this quantity is something which we can call it as delta E inter. Yeah, so that is the inter, that is basically the molecule surface interaction, and this delta E intra is basically talking about the molecule interaction. So, now you see how complex the potential energy surface is. The potential energy surface itself containing the molecule distance, the relative orientation of the molecule with respect to other molecule, the relative orientation of the molecular axis with respect to that of the surface lattice, and so on. So, there are much more parameters, much more coordinates that one need to actually just consider if you want to finally understand the so called adsorption energy or the interaction energy of the molecule on the surface. So, in general, in any case, the total adsorption energy would basically be again a sum of the delta E inter plus the delta E intra. So, that is remaining the same, but the point is to understand the delta E inter and the delta E intra, it is a bit more complex, because one need to consider more possibilities to finally write down the adsorption energy, because the adsorption energy is something that you would finally say how strongly the molecule is basically binding onto the surface and also within the self assembled pattern or the self assembled Adlayer on the surface. And that is basically the case, but now you will also see that in the next example that this is clearly the point at the so called molecule surface interface, but when the molecule surface interface is actually getting much more thicker, that means when you are depositing multi-layer, then the influence of the surface is actually getting much more reduced, and then everything is basically going to be controlled by only the so called delta E intra. But there you have to also see some additional factors may also come into play, that the molecule may also just start to orient in dimension as well, and not simply like on the surface where we have seen that a planar molecule was just orienting with respect to the surface. Yeah. So, that is actually the case. But generally, like when you start to make thicker layers, everything is basically controlled by the molecule interaction, and the molecule surface interaction is kind of irrelevant in that case. Yeah. So, that is the kind of summary. Now, if you put everything together, I have again the same molecule, the iron thiocyanin molecule. Now, you can see the molecule, and this is actually a coverage which is much higher. So, it is about 1 monolayer coverage. There you can see all the molecules are now coming together and forming this nice, very well ordered pattern, as you would find here. So, the molecules are nicely arranging like this, where you can see the azimuthal orientation of the molecule is about 30 degree. Yeah. So, that is something what you can define here. So, this is basically the lattice, and this is somewhat the orientation of the molecule, and this is about 30 degree, for example. Yeah. So, approximately 30 degrees the azimuthal orientation of the molecule. So, that orientation comes due to the fact that this orientation actually allows the molecules to interact with the maximum surface area, because the intermolecular interaction in this particular case is van der Waals type of interaction, and therefore, the molecule always try to arrange in a way where there is maximum overlap between the molecular between the molecules. So, that is the basic key of this. Yeah. Now, but the point is, in the STM image, so this is again a scanning tunneling micrograph image. So, there you cannot see the details, but using some additional experimental parameters, you can clearly determine what is the adsorption geometry of the molecule. But then it turns out to be that not every molecule is basically adsorbing at the same type of adsorption geometry or same type of site. Instead, it also has something like a supercell, which is basically 1, 2, 3, it is a 3 by 6 supercell what the molecule is basically forming. Yeah. Because you would find that this particular molecule is adsorbed at a given site, but when the molecule is actually arranging in the lattice, you can see that the center atom, you can pay attention to the atom at the center, is basically just moving away from the bridge site, because here the central atom was actually at the bridge site, and as the molecule moves along the lattice, you would find that the bridge site is basically just changing, and then finally at the 7th molecule, the molecule retain the original adsorption geometry as the one at 1 position. Yeah. So, that means there is again a super periodicity along both the crystallographic direction, and along the other crystallographic direction, the super periodicity is basically about 3 times of the molecular lattice, and along the other direction it is about basically 6 times of the molecular lattice. So, it is not just that we can say that this is the unit cell that defines the molecule, it is indeed the other red dashed line represent basically the molecular lattice. So, that means what is going on at the interface is even more complex than what you would imagine in the case of atomic adsorbates, but nonetheless it is kind of an extremely interesting topic to investigate, and using microscopy like you see here, one can understand things at the atomic scale, and that will actually just help you in understanding a greater detail or and kind of clearly the molecule surface interface. So, this would be kind of a complete picture of the molecular adsorbate on the surface or directly at the interface. Now, what I want to also do okay, before that what I would like to also show you are some additional factors that are going to actually just control the molecular self assembly on surface. So, so far what we have seen is that it is basically controlled by the molecule orientation and also the molecule surface orientation, but that is not the case, because you would also find that in certain cases or in many cases in the case of molecule, that depending on the coverage of molecule that you have on the surface, here for example, I have 0.7 monolayer coverage, then I have increased the coverage to 0.8 monolayer, then 1 monolayer. So, depending on the coverage, you would find different type of pattern. So, you can see here the first pattern, it is again a thiocyanin molecule, but the central metal atom is cobalt in this case, that is the only difference. But what you find is that here the molecule again orients somewhat like what we have seen in the previous case. But when you increase the coverage, you find extremely interesting pattern. So, you can see here a very interesting pattern is basically emerging, and then when you increase the concentration or the coverage very high, then the molecules are actually going down to something like an extremely close packed pattern. So, the point here what I want to mention is, again it has to something to do with the so called possible molecular orientation and the stabilization energy, or the so called interaction energy through the molecule interaction is the key for it. And that you can clearly control by the concentration. So, depending on how much molecule you dope or how much molecule you deposit on the surface, you can actually just decide what type of Adlayer pattern that you would like to have. So, that is something quite controllable in the case of molecule, but in some cases there are only subtle differences between these energies, and therefore, like control is not as easy as one would imagine. But if there is a clear difference between the different minimas in energy, then one can easily control these patterns on surface using concentration, for example, or in some cases one can also use temperature as a control parameter. You can also just generate different type of molecular pattern on the surface. Now, I would also like to discuss with you a little bit away from the surface. So, what happens if I would deposit molecules in a multilayer? Of course, I am not going to consider in my class something like several layers. So, that is something we are not really considering, at least in the microscopy part. But what I am going to show you here is actually a coverage which is 1.7 monolayer. Yeah. So, this is again the iron phthalocyanine on silver 111 surface. So, it is the same example as you have seen in the previous slide. Here I have basically the first layer, then the second layer and the third layer and so on. Yeah. So, this is clearly like a part where I have an overlap between the first layer and the second layer. So, here you can see in the first layer clearly the molecules are arranging like this, which we have already seen. It is nice. So, they are basically just doing this nice compact packing of the Adlayer in the first layer. And now, in the second layer, what you find interesting is that microscopically you are unable to image the entire part of the molecule. So, that is what is shown here in this scheme. What you find is that you are only able to just see some part of the molecule. Yeah. So, that actually gives rise to an impression that they are actually just kind of overlapping, but that is not really possible that two molecules just overlap like that, unless and until they have some kind of a tilted orientation. So, if you have a tilted orientation and when you look from the top, they are basically appearing like one molecule is overlapping on top of the other. Yeah. So, then what happens is that in the first layer and in the second layer, you would find that the molecular orientation with respect to the basal plane of the surface is actually changing. So, in the first layer, all the molecules are planar with respect to the surface, and in the second layer, of course, the molecule is planar, but the molecular orientation with respect to surface is not anymore planar like this. It is basically getting tilted with respect to the basal plane of the surface. That is interesting. So, the molecule is getting tilted, and this is kind of a side view and this is the top view. You can clearly see in the top view that how the molecular orientation is basically happening. Now, the interesting thing that you would ask, why is basically suddenly the molecule is changing their orientation? Why not just the molecule pack in the same way as you would actually just see it in the first layer? Well, that is an obvious question, but the interesting thing is that when the molecules start to pack in the multilayer, they start to increase the so called molecule-molecule interaction. And for molecule like phthalocyanine, which has actually a strong pi electron cloud around the molecule, it is very well known that the molecules are actually some kind of having a strong pi-pi interaction. So, if you want to maximize the pi-pi interaction, what the molecule does is they tilt themselves in order to maximize the so called molecule-molecule interaction, which is again a pi-pi interaction, van der Waals interaction, but they try to maximize it. So, how do you clearly say that this is the case, we can understand that if you look at the bulk structure of these kind of phthalocyanin molecules. So, this is basically the packing of copper phthalocyanin crystal, that means the 3-dimensional crystal of copper phthalocyanin molecules, and there people find different type of packing of copper, which is known as alpha copper, beta copper PCO, epsilon copper PC. These are just names, and there they are all basically having some kind of tilted orientation, but the slight differences in the relative tilt, that is the only difference between the different phases. But in all the cases, what you have effectively is the so called pi-pi interaction, and to maximize the pi-pi interaction, the molecule actually just get tilted with respect to each other and they pack. And you clearly see when I form the multi-layer, so that means already in the second layer, the second layer molecule already is tilting with respect to the surface. So, that is something you can already see, and if I would basically grow molecules into the multi-layer, then their tilt would become larger, and then it will basically just remain like in the bulk packing. Yeah. So, that is the connection between the interface and the bulk packing. So, they are always related, but at the interface there is a strong influence of the surface, and therefore, the molecule surface interaction prevails at that point at the interface, and therefore, the molecules are actually just looking more or less flat adsorbed on the surface. But as you go thicker and thicker, the molecular orientation is changing and they start to basically follow the bulk packing. So, that is the interesting aspect that one can basically see here. Now, if you would basically want to finally make a comparison of the solid atom interface and also the molecule solid interface, like we see it right now. This is of course a qualitative picture where one can kind of relate the typical relation between the adsorption energy of an atom like adsorbate on surface or like a molecule like adsorbate on the surface. So, the interesting aspect about the atom like adsorbate on the surface is that they are strongly bonded to the surface. So, like we have already seen, so they are typically bonded strongly onto the surface. So, in many cases you would even find chemisorption would happen, and because of that there is a strong chemical interaction between the molecule and the atom and the surface. Your typical binding energy or the so called adsorption energy is several orders of magnitude higher than that of a typical molecule surface adsorbate. Yeah. So, that is what we try to show here on a relative energy scale, where 0 is actually a non-interacting adsorbate on surface. That means an adsorbate which is really far away, but as you put this the adsorbate on the surface, so they start to interact basically in a strong way. So, obviously you would find that the atom like adsorbate has the highest binding energy or adsorption energy on surface. Yeah, that is because of the true chemical interactions between them, and that actually, as we have already seen in a few cases, it can actually vary from a few electron volt, for example. So, you can actually have it in the order of a typical chemical bond like 2, 3, 4 electron volt is the typical order. But now, when you actually just take atom like molecules, so these are actually molecules that would basically just go on to the surface, but you can see a carbon monoxide would adsorb on the surface like this. Yeah, and that is also looking like an atom like adsorbate because they are small, and then their adsorption energy is also very high because they also would form a strong chemical bond or some kind of a chemisorption. I am just calling it a CS, chemisorption between the atom and the surface, and in that case also you would find that the energy, the so called adsorption energy, is actually in the order of a few electron volt. Yeah, so that is the point that you need to consider. But when the molecular size increases, so that is something that what I have here depicted as a diameter of the molecule. So, of course, the diameter of the molecule is quite hard to define, but it is typically something to do with the area of the molecule that is in fact interacting with the surface. Yeah. So, for a benzene molecule, the hexagonal area itself is the diameter of the molecule, and for molecule like this, it is typically a bit hard to understand, depending on whether the molecule goes like this or the molecule stands up and so on. But something like, we can roughly say the area of contact of the molecule is something we can call it as a diameter. And now that is something quite important when it comes to the bigger molecule. And the point what I want to show here is that as you go to bigger molecule, of course the diameter basically increases, and you would also find that the adsorption energy is basically decreasing, yeah, with respect to a non-adsorbed state. So that means atom like adsorbates or atom like molecular adsorbates are having a very, very high adsorption energy, truly because they do some kind of chemisorption on the surface. It is in the order of a few electron volt. But when it goes to molecule, as you have already seen in the case of phthalocyanin, the interaction energy, it is of course a rough calculation that I have done, but the interaction energy is typically in the order of a few hundreds of milli electron volt. Yeah. So just to give an analogy, so it is not very quantitative. So 100 milli electron volt, and typically here you have something like 3-4 electron volt. So that is the typical order that we can talk about. Yeah. So then people generally call it, it's actually something like a quasi epitaxy. It is not really an epitaxy, because epitaxy has to really do something with the surface. Here molecule is not really necessarily following the surface, so then you cannot call it really as an epitaxy. Therefore, in some cases people also refer to it as a quasi epitaxy. Yeah. Now there is also one more interesting factor or parameter that you can plug in, that is basically the strain that we talked about. So in the case of atom like adsorbates, although we talked about a variety of strain, you might notice that the strain that if you would calculate basically in the case of molecular adsorbates is much larger than in the case of atom like adsorbates. Yeah. The reason is very simple. The lattice mismatch of a molecular adsorbate with that of the surface is enormous, is very large, yeah, because you have to consider the entire molecular dimension, and the lattice of the surface is basically very small. So that is the reason why you would find that the so called strain is in fact increasing in this fashion. It is a qualitative measure, and then typically these kind of molecular epitaxy is kind of strained van der Waals epitaxy. And within this itself, van der Waals epitaxy, or the one where the molecules are stabilized by van der Waals interactions, are the one with the lowest adsorption energy. But if you have like strong hydrogen bondings or ionic bonds that would play inside, then you could also just get into something like 1000 milli electron volt. So that is actually possible. Yeah. So that is the range what we are talking about. So like van der Waals epitaxy, typically a few hundreds of milli electron volt. If it is hydrogen bond, you can reach up to an electron volt, and if it is basically strong chemical bonds that is forming between the adsorbate and the surface, then it is basically 3 to 4 electron volt, or a few electron volt is possible. So that is the order of energy that we are talking about. But in generally, you can kind of understand the solid atom interface and the solid molecule interface using this kind of a qualitative plot. Yeah. You can also just read this article. It is an old review article, nonetheless it gives a good summary about molecular adsorbates on surface. You can get a certain important aspects about the preparation and the energetics of molecular adsorbates on surface in this particular review article. Yeah. Now what I want to actually discuss with you is the molecular Adlayers that are formed at solid liquid interface. So this is slightly different, because so far what we have been discussing is actually molecular adsorbates on solid surface, and this was actually kind of a solid state film. But now what you can also do, so this is basically you are seeing is a scanning tunneling microscope itself, which is capable of imaging molecules inside a liquid. So that is the point. So now what you have additionally is you have the surface, this is the surface, and then you have the molecular adsorbates. You can see here they are packing, and then you have the a sharp atomically sharp tip of the scanning tunneling microscope, and it basically scans on the surface and try to image the molecule inside the liquid. Yeah, so that is the interesting aspect here. So, in this particular case, of course, molecule do self assemble on the surface, but interesting fact is that the molecules are actually the solvent that we use is actually going to play, the concentration of the solvent is actually going to play and the nature of the solvent is going to play a strong role in basically just getting the right type of molecular assembly on the surface. Just to keep it in mind that one need to have like these kind of low dielectric constant or low vapor pressure liquids typically to do the study. This we will revisit when we study the scanning tunneling microscope. So, then you will understand it a bit more in detail, but right now I just want to tell that the typical solvents that we are going to use, so the so called liquid phase medium that we are using is actually fatty acids or fatty alcohol or phenyloctane. These kind of alkyl chains we are using typically for the as a solvent or the liquid medium. Now, let us have a look. This is very simple. So, some STM images of different type of molecules that we can form in the solid liquid interface. So, you can see depending on the type of functional group and also where you place the functional group. Here you can see it is a para dicarboxylic benzene, and this is a meta dicarboxylic benzene. So, depending on the position of the carboxylic group, you can see they are arranging either in a linear fashion or in the case some kind of a zigzag fashion that is basically allowed by the symmetry of the molecule. So, you can nicely image molecules at the interface. Now, the interesting thing is again here this is actually the trimesic acid molecule which we have already discussed, and we said that this molecule can form either a dimeric hydrogen bonding or a trimeric hydrogen bonding. Yeah? Trimeric hydrogen bonding or dimeric hydrogen bonding. So, these are the two ways that the trimesic acid can interact with respect to each other, and depending on this interaction you can either form a flower structure or a chicken wire structure. But now, the interesting aspect what I want to show you is like all this imaging is basically done inside a fatty acid. Yeah. Now, depending on the type of fatty acid that you choose, yeah, either you choose actually long chain, really long chain fatty acids like octanoic acid or nonanoic acid, then you would find that the most favorable pattern is basically chicken wire pattern. And if you would use basically low a smaller alkyl chain length fatty acids like pentanoic acid, hexanoic acid and so on, then you would find that the flower structure is actually the most preferred one. And somewhere in between the so called borderline between these two, the heptanoic acid, you find mix of both chicken wire and flower pattern. So, you clearly see the nature of solvent is playing a very crucial role in this case in controlling the type of Adlayer pattern that you form on the surface. Yeah. It is all to do with the length of the chain, because in the case of chicken wire it is also observed that the molecules, the solvent molecules itself also get trapped inside these kind of pores, yeah, and that is being stabilized by the long chain is the origin of this different type of pattern. But important aspect what I want to say is like the nature of solvent. Now, what you also can do is you can basically increase the concentration. Now, what I am doing is I take again octanoic acid, trimesic acid, but what is expected is that this molecule only form this chicken wire pattern. Yeah. So, what is the pattern in octanoic acid as per the previous literature. But now, interesting thing, by doing sonication, so you mix a certain amount of molecule inside the solution, make a saturated solution. Now, if you sonicate it for longer time, that is what is given here 0 hour, 2 to 4 hour sonication, 4 to 5 hour, 5 to 7 hour sonication, then what we find is that the concentration of the molecule can be increased if you do increasing the sonication. And then what we find interesting is that when you increase the concentration of the molecule in this liquid phase, then we suddenly find that you can find both the flower and the chicken wire pattern. So, that means concentration is also playing an important role in controlling the Adlayer pattern. So, finally, What I also want to say is that again this is the trimesic acid molecule which is worked out in octanoic acid. So, the octanoic acid, and what is interesting here, depending on the temperature at which you image the molecule, you also find that you can basically find the chicken wire and the flower structure depending on the temperature. So, finally, what I want to say, like when you do the solid liquid interface, it is not just the geometry or the shape of the molecule matter, it also matters the concentration, the solvent in which you are imaging the molecule, or the temperature at which you are imaging the molecule, all actually plays a role, and therefore, you have actually much more important factors that are controlling the self assembly of molecule in the case of molecule solid liquid interface. Yeah. So, that is in general about the molecular adsorbates, and in the next class we will look at these examples again using different kind of microscopy, and we try to understand additional aspects about these kind of adsorbates. Yeah. Thank you very much for your attention.